In this module, we introduce phase diagrams of pure substances. In general, a phase diagram is a graphical representation that summarizes the phase behavior of a system in specific coordinates. It indicates which phase or phases are the most stable under particular conditions. In this course, we will focus on PT diagrams of pure substances. They utilize pressure and temperature as their coordinate axes. These diagrams serve as maps outlining the regions of thermodynamic stability for various phases of the substance in temperature and pressure coordinates. It is essential to understand that just because a state is indicated as stable under certain conditions, it does not guarantee an immediate appearance of that state in the system when those conditions are established. Achieving equilibrium can sometimes be a lengthy process, especially when transitioning between solid phases. This can lead to the occurrence of metastable states. While these states aren't the most thermodynamically stable, they can persist for a long time because their transition to a more stable state is exceptionally slow. Now, let's look at a typical PT phase diagram of a pure substance. Both pressure and temperature are intensive variables, which means they don't depend on the amount of substance present. For any system, we can externally set specific values for both pressure and temperature. Therefore, there are no gaps on a PT phase diagram. On the phase diagram, you will notice distinct regions, boundary lines, and specific points. Each region is labeled by the phase that's most stable for a given pressure and temperature. The boundary lines and points indicate equilibrium between phases. Let's go deeper into understanding why a specific phase is represented by a region in the phase diagram. As we are discussing pure substances, we are dealing with a single component system, which is denoted by C equal to 1. So, if there is only one component and one phase present, how many degrees of freedom do we have in our system? The answer is 2, represented as F equal to 2. There are two independent intensive variables that can be varied without altering the phase state of the system. This derivation emphasizes that a single phase in a one-component system is represented by a two-dimensional object, a region, on the phase diagram. In the context of our PT phase diagram, these variables are pressure and temperature. So, in a phase diagram, each region represents a specific phase, be it solid, liquid, or gas. Within the regions of the diagram, we can adjust both pressure and temperature, and the system will remain in the same phase. Going further, you will also notice on a phase diagram certain curves separating these phase regions. These are coexistence curves. In a scenario with one component and two coexisting phases, the number of degrees of freedom becomes 1. This means that in a one-component system, the states corresponding to equilibria between two phases are represented by a one-dimensional object, a curve. Consequently, we are left with just one independent variable that can be modified without affecting the phase state. If the current state of the system is on a coexistence curve and we decide to alter the pressure, the temperature has to be adjusted accordingly to maintain the two-phase equilibrium, ensuring that the system remains on that coexistence curve. Now let's discuss a distinctive point on our phase diagram, the triple point. Given a single substance, if three phases coexist, how many degrees of freedom are there? The answer is 0. This means that neither the temperature nor pressure of the system can be varied without altering the phase state of the system. The triple point is where three coexistent curves intersect, denoting the unique set of conditions where three distinct phases of a substance, usually solid, liquid, and gas, are all in equilibrium. This point is intrinsic to the substance and is characterized by the triple point's pressure and temperature, which are unchangeable for a pure substance. As we can see in the figure, the triple point specifies the minimum pressure at which a substance liquid phase can exist. Moreover, if the slope of the solid-liquid coexistence curve is sloped forward, as it is typical in most PT diagrams, the triple point also designates the lowest temperature permitting the existence of the liquid phase. An important part of the phase diagram is the critical point. This point marks the termination of the liquid-gas coexistence curve. The critical point is defined by the critical temperature Tc and the critical pressure Pc. The distinct boundary between the liquid and gas phases cease to exist at the critical point. Let's take a closer look at what happens. When a liquid is heated in a sealed container, as shown in figure A, we observe that the density of the vapor phase increases. Conversely, the density of the liquid slightly decreases due to its thermal expansion. As the temperature continues to rise, there is a critical stage depicted in figure C, where the vapor's density equals the liquid's density. At this point, the interface between the two phases vanishes. The temperature at which this interface disappearance happens is the critical temperature Tc, and the associated vapor pressure is the critical pressure Pc. Above the critical temperature, the distinct phases of liquid and gas merge into a single homogeneous phase termed the supercritical fluid. The supercritical fluid is a state exhibiting properties intermediate between liquids and gases. This phase has unique characteristics, making it of particular interest in various scientific and industrial applications.